Welcome to this edition of Lakeside Physics. In this video, we will introduce you to the concept of work. We'll imagine a situation in which a box of mass m is resting on a frictionless level surface. A horizontal force F is applied to the box. What happens? Well, obviously it begins to move. What kind of energy does it gain? The energy of movement we call kinetic energy. Where did this energy come from? Well, it must have somehow been gained due to this force F. Now, we can imagine a situation in which instead of the force being applied horizontally, the force was applied perpendicular to the surface. Would it still have gained kinetic energy? The answer to this is no, it wouldn't have moved. So this is all related to this concept of work. So what is work? Work is the energy gained or lost by an object due to a force. Work is equal to the force parallel to displacement times the displacement. And this is a good equation to have on a note card. Work equals force parallel times displacement. That's what those little two bars means, is parallel. You can also say that work is equal to force times the displacement times cosine of theta, where the theta, the angle, is between the force and the displacement. It is a scalar, so even though it is being made by two components that are both vectors, the final product is a scalar. This is actually a dot product for those of you that have worked with vectors before. The units are force times distance, or newtons meters, which is going to be redefined as a joule. And 1 Newton meter is equal to 1 joule. So some thoughts on this. First, if an object doesn't move, work is not done on the object. There has to be some displacement. If a force vector acts perpendicular to the object's displacement vector, the force does no work on the object. If a force vector acts in the same direction as the object's displacement, the work done is positive. This means the object is gaining energy. If a force vector if a force vector acts in the opposite direction of the object's displacement, the work done is negative. This means that the object is losing energy. Note, if you are using work equals F delta x cosine theta, the negative sign appears because cosine of 180 degrees is -1. If you are using work equals force parallel times displacement, you need to recognize your work should be negative if the object and the object's displacement and the force are in opposite directions. So let's start with an example. A 15 kilogram box is being pulled 3.0 meters across a level floor by an applied force of 50.0 newtons, pulling at an angle of 36.87 degrees above the horizontal. A frictional force of 15 newtons resists this motion. Find the work done by each of the forces acting on the box. Go ahead and pause the video and give this a try, and then let's take a look. First, we want to draw a free body diagram so we can see all the forces acting on the object. So here's our free body diagram. Next, we want to start by finding the work done by the applied force, which is going to be the force applied parallel times delta x. Notice that the parallel component is only 40 newtons times the 3 meters, and we're only using that portion, so we end up getting that the work applied is 120 joules. Now, let's find the work done by friction. The frictional force is 15 newtons times our displacement, and again we're going to multiply by the -1 to represent that the force vector points in the opposite direction of the displacement vector, and we get the work done by friction as -45 joules. Now, the work done by the normal force is going to be 0 because the normal force is perpendicular to the displacement. There is not a parallel component. This will also be true for the work done by the weight. Notice that the total work done by the forces is positive. If we take the work applied plus the work done by friction, the normal force, and the weight, we get a total of 75 joules. The box has gained energy. Let's do another example. A person lifts a 16 kilogram box which is at rest from the floor and places it at rest upon a shelf that is 2.0 meters above the ground. Assume g equals 10.0 meters per second squared. What is the work done by the person on the box? Well, first we need to know how much force is needed to lift the object. Now, if we imagine that initially to lift something, we would have to apply a force bigger than its weight, and then as we lift it up, if we were to lift it up at a constant speed, we would apply a force equal to the weight, and then as we had the object come to a stop on the shelf, we would need to apply a force that was a little bit less than the object's weight. We could imagine that this might all average out to be essentially equal to its weight. So we will assume that the force the force needed is equal to its weight. So we get that the work done by the person is 320 joules. Now notice that this is positive because the applied force and the direction of motion were in the same direction. Now, how much work did gravity do on the box? Well, the force of gravity times the displacement times -1 is negative 320 joules. Again, notice the negative sign is added because the force vector points in the direction opposite the displacement vector. This means that the force of gravity was taking energy away from the box. How much GPE did the box gain? Well, gravitational potential energy is equal to mass times g times the height, so we get 16 kilograms times 10 times 2, and that's equal to 320 joules. Notice that this energy the box loses due to the gravitational force is actually not really lost, but stored as gravitational potential energy. So in summary, gravitational potential energy is the energy stored by the work of the force of gravity, and elastic potential energy is the energy stored by the work of the force of a spring. Alright, let's do a third example. A 1.2 kilogram puck is sliding to the right along a level surface. Friction slows the puck to a rest over a distance of 4 meters. What was the total work done on the puck? So again, you can try pausing this video and try completing this problem. It should be clear that only the force of friction is going to do work on the puck. The normal force and the force of weight are both perpendicular to the motion, so therefore will do no work. Now the work done by the force of friction is equal to the force of friction times delta x, or the coefficient of kinetic friction times the normal force times the displacement. Notice we put this times -1 in there because we know they're in opposite directions, so the work done should be negative. So we end up getting that the work done by friction is -12 joules. Notice that the puck has lost energy due to the force of friction. How fast was the puck traveling initially? Well, we're essentially looking for trying to find the initial velocity. We know that the final velocity will be 0 and that the displacement was 4 meters. To solve for the initial velocity, if we had the acceleration, we could find it. Well, we can use forces to find acceleration. You know the sum of the forces is the negative the force of friction, so if we plug our numbers in, we can solve and find that the acceleration would be -2.5 meters per second squared. Using our fourth kinematic equation, v squared equals v naught squared plus 2a delta x, we can solve for the initial velocity, initial speed, and we get 4.5 meters per second. Notice that the puck slowed down. Perhaps work is related to this movement. Let's come back to work and think about how this might come in to play. Well, we know that the work is equal to force parallel times the displacement. Turns out we can also think about this in terms of the total work. So the total work will be equal to the sum of the forces parallel to the displacement times the displacement. This will also be equal to mass times acceleration times displacement. And if we recall the kinematics equation we just used, here, if we replace a delta x with v squared minus v naught squared over 2, we end up with this equation, which relates back to kinetic energy. Recall kinetic energy is equal to 1/2 mass times speed squared. So essentially, the work done is equal to the final kinetic energy minus the initial kinetic energy, or the change in kinetic energy. This is called the work energy theorem. that the sum of the work done is equal to the change in kinetic energy. Notice that if the total work done on an object by all the forces is positive, the object speeds up. If the total work done by all the forces is negative, the object slows down. And finally, if the total work done on an object by all forces is 0, the object maintains a constant speed. This equation is really what defines kinetic energy. And it's really not actually all that useful. We will often be using an idea called conservation of energy to duplicate the results of the work energy theorem. Let's go back and check this idea of the work energy theorem to make sure it actually works. So we had said that the total work done should be equal to the change in kinetic energy. So if we take the work normal plus the work due to the weight plus the work due to friction, it should be equal to this change in kinetic energy. We had negative 12 joules. We plug in that our final velocity should be 0, and we solve and we get that the initial velocity was 4.5 meters per second, just as we had already solved using kinematic equations and forces. Let's end this video with one last example. An object moving in one dimension experiences a force that varies with the distance traveled. A graph of the force versus distance is shown below. How much work was done by this force? Well, there's kind of a problem. Our work equation assumes that the force is constant during the displacement which we are interested. If the force varies, we cannot solve for work mathematically without using calculus. But if we have a graph, we can use the ideas of calculus, the idea of looking at the area under a curve. For this case, our area under a force versus displacement graph is the work done by the force. The area below the displacement axis is negative. So if we had something where the force was negative, we would end up having a negative work done. So we can solve for the work done by this particular force by looking at the area under the curve of a force versus displacement graph, and in this case that will be our displacement of 3 meters times the force, 16 times 1/2, since it's a triangle. So we get 16 times 3 times 1/2 gives us 24 joules. That ends our video for today talking about work. If you have any questions, please let us know. Thanks.